Assalamu alaikum everyone. Today I'm going to be giving a review lecture on lung volumes. This is P17. So let's start here. So these are the learning objectives. We're going to have to know the lung volumes, the lung capacities, and the volumes that are modifiable. And we're also going to be able to identify them on a spirogram. And then we're also going to be able to you have to be able to measure the inner, you know what the inner gas dilution method to measure the residual volume. And then the ideal gas law and the effect of pressure on temperature on the volume that we measure, pathologies which can decrease the vital capacity, and the difference in the effect of lung volumes between obstructive and restrictive lung diseases. Okay, so first we're going to start with the four lung volumes, and this is pretty easy. Like this whole diagram explains everything. First, we have the residual volume, which is the volume of air that when you fully expire, when you get rid of all the volume here, this volume of air that remains in your lungs that you can't get rid of is the residual volume, and it's about 1.5 liters. Next, we have the expiratory reserve volume. The expiratory reserve volume is the volume of air that you can maximally expire after a normal expiration. So after you do a normal expiration here, it's the volume of air that you can maximally expire. And it's also about 1.5 liters. It's listed here B. Okay, and then we have the tidal volume. The tidal volume is just going to be the volume of air that you can inspire when you expire and expire that when you're breathing normally. So this is just normal breathing, and it's about 0.5 liters. Inspire and expire 0.5 liters when you're breathing normally. Okay? And then lastly, we have the inspiratory reserve volume. For the inspiratory reserve volume, it's the volume of air that you can fully inspire after a normal inspiration. So when you inspire normally here, from here to here, it's a volume of air that you can inspire even more to completely fill the lungs. This is the inspiratory reserve volume. And remember, the ones that are modifiable are going to be all these ones, right? The ones here. The only one that's not going to be able to be modifiable is the residual volume. The residual volume, you cannot change it. It's always going to be in the lungs. And it's the only one that you can't measure using a spirometer. All the other ones you're going to be able to measure using a spirometer. I'm going to show you right now. Here you go. So this is a spirometer. And in a spirometer, as you can see, this part is not going to be clear. The residual volume right here, it's not going to be clear. But you're going to be able to notice that these small waves, that's going to be the tidal volume. Yeah, the tidal volume. And then this part from here to here, when someone maximally inspires, is going to be the inspiratory reserve volume. When you expire after a normal expiration, when you fully expire after normal expiration, is going to be the expiratory reserve volume. And yeah, we're going to talk about the vital capacities later. So I just wanted to show you this. This is a spirogram, and you're not going to be able to see the residual volume using a spirogram. So now this is how you measure the residual volume. Use a special method called inner gas dilution. Um, So basically what we do is we add helium into the spirometer, And when we add the helium into the spirometer, we measure that concentration. So let's say the spirometer volume is going to be Vs, and the concentration of the helium is going to be C1. Okay? And then we have to tell the patient to maximally expire. Okay? We have to tell them to maximally expire, and then we attach the mouthpiece of the spirometer to the patient. And then we let the patient breathe normally in the air using the air from the spirometer. And then after a while, we'll measure the concentration of the helium, which is diluted now because it's distributed to the to the spirometer it's also distributed to the residual volume now. So it's distributed to the spirometer volume and the residual volume. So we've added a new volume. So now we can use the formula where the concentration times the volume of a place of a thing, it will equals to its new concentration times the new volume. This is always true for everything. This new volume V2 will be equals the spirometer volume plus the new reserved volume that when we attach the patient to the only volume left in his lungs were the residual volume. So that's why this is going to be the residual volume. And this is why it's very important to tell the patient to expire maximally. Otherwise, you wouldn't actually be measuring the residual volume. You'd be measuring something else. For example, if you tell the patient to maximally inspire, you'd be measuring the total lung capacity and not the residual volume. So when we rearrange this formula, we get RV is equal C1 times VS over C2 minus VS. You can rearrange this. This is how it's written in the notes. VS times C1 minus C2 over C2. And you're going to get the residual volume. Okay? Next are the lung capacities, and the lung capacities are basically just a mixture of the lung volumes. For example, the inspiratory capacity, which is this one right here, this green one, the dark green one, is going to be the tidal volume plus the inspiratory reserve volume. And it's basically the volume of air that you can maximally inspire after you do a normal expiration. So normal expiration, and it's the volume of air that you can maximally inspire. Next, we have the functional residual volume, which is you can kind of define it as the volume of air that remains in your lungs after a normal expiration. So when you expire normally, the volume of air that remains in your lungs is going to be the functional residual capacity. Okay? and and it's going to be equals the expiratory reserve volume plus the residual volume. Next, we have the vital capacity. The vital capacity is going to be the volume of air that when you the volume of air that when you inhale, when you forcefully exhale out all the air in your lung, not all the air, obviously it's going to be residual volume, but we don't, it's not part of the vital capacity. When you exhale maximally, and then you inhale maximally, that volume of air that you inhaled maximally after exhaling maximally is going to be the vital capacity, and it's going to be equals the expiratory reserve volume plus the tidal volume plus the inspiratory reserve volume. Okay? And then lastly is the total lung capacity, which is all the volumes of the lung combined together. So the inspiratory reserve volume plus the tidal volume plus the expiratory reserve volume plus residual volume. It's the total volume of air in your lungs that can be in your lungs, right? The total volume of air that can, maximum volume of air that can be in your lungs. All right. Now we're going to talk about the ideal gas law, and this is not that important, but there is some things that I want to tell you is that the ideal gas law, PV equals nRT, it shows P is the pressure, V is volume, and the other ones you don't have to know, but N for your information, N is the number of moles, R is the constant, it's 8.31, and T is temperature in Kelvin. So you don't really have to know that, but all you have to know is that when we measure different volumes, the volume is going to be affected by the pressure and the temperature, right? These are constants. The pressure and the temperature are going to affect the volume. So we always have to consider the temperature and the pressure, where if you see V is equals nRT over P. So a higher P would cause a lower V, and the volume would increase at a higher temperature because it's proportional, and at lower pressures. And also, not only that, but also the amount of water vapor, which is pH2O, could also affect the volume. So you could also have to consider that. There's three conditions which we have to know. BTPS, which is body temperature pressure standard, and it's basically the volume that you're going to measure that's going to be inside the body. Okay? And then there's ATPS, which is the volume measured by the spirometer. So when we measure a volume by the spirometer, we're going to get the ATPS. And then we have the STPD volume, which is the temperature when the temperature and basically in dry air, right? The volume in dry air. And this is important because, for example, when we measure the ATPS, we're not measuring the actual tidal volume inside the lungs. We're just measuring the volume that's written by the spirometer. So we have to convert that ATPS into BTPS so that we can get the actual volume inside, like inside the lungs. So you don't actually have to know the conversions or anything. Just know that yeah, they exist. And obviously, BTPS, what would be the temperature? It would be the temperature of the body, about 37 degrees Celsius. ATPS would be the temperature of the spirometer. And STPD, the temperature would be 0 degrees Celsius. Okay? Now, the effect of age on vital capacity. So what is going to be the effect of age on vital capacity? Well, this graph here like summarizes it pretty well. From zero, like from birth to 20 years old, there's going to be an increase in all of the lung volumes, and even the residual volume is going to increase, but not by a lot. So there's going to be an increase in the vital capacity. Between ages to 20 and 60, there's not going to be the residual volume is going to remain like partially constant, and the total lung capacity is going to also remain virtually constant here, as you can see. And then above the age of, so it's not going to, here, the vital capacity is going to remain constant. Above the age of 60 is where the residual volume starts to increase. And when the residual volume starts to increase, you can see the total lung capacity is not increasing with it, causing the vital capacity to decrease. So the total lung capacity remains constant, while the residual volume increases, causing the vital capacity to decrease above the age of 60. That's it for this one. And here are causes of reduced vital capacity. You don't have to know the conditions, but you do have to know that, a skeletal abnormality could cause a reduce in vital capacity. Weak respiratory muscles could cause a reduce in vital capacity. Lung diseases could cause a reduce in vital capacity. And severe airway obstructions, like asthma, chronic bronchitis, could cause reduce in vital capacity. That's all you have to know about this slide here. So let's move on to the next one. Here are the effects of lung volumes during different lung diseases. Oh, spelled diseases wrong. Excuse me. Okay. So the effect of lung volumes during different lung diseases. So there's two different lung diseases that you have to know is the obstructive lung disease and restrictive lung disease. So this is a table that summarizes it completely. In obstructive lung diseases, the TLC is going to increase. The residual volume and the capacity, the FRC, which is the functional residual capacity, is going to increase higher. It's going to become even, it's going to increase more than the TLC. So that means that the ratio of RV over TLC, the percentage ratio, is also going to increase. Why? This is because you increase this more than you increase this. The increase of this is going to be higher than the increase of this. So the RV is at top, the TLC is bottom. Yes, the higher TLC will cause this to reduce, but since this is also increasing, but it's even increasing more, it's actually going to cause it to increase. Okay? For restrictive lung disease, the TLC is going to become lower, the FRC is going to become lower. And since they're both become lower, and it's not like this one becomes more lower than the other, they both decrease relatively by the same amount, the RV over TLC ratio will be relatively the same and it won't be affected. Okay? So that's basically this entire lecture. Um, yeah, thank you if you hope you guys understood everything. Yeah, bye.